Okay, thank you very much. It's really a great pleasure to be here. Well, not only at the Schrödinger Institute, but in this room, which I think at the time of those programs, it still didn't bear the name of Boltzmann, this room. Yeah. Okay, so I actually gave a talk with the very same title several days ago in Graz. And since Klaus was there as well, I will organize this talk slightly differently so that I will skip the historical part and instead, yeah, but, well, instead I will begin this talk with a description of a class of measures which will later play the crucial role when talking about stationarity. So let me begin with the description of what can be called multiplicative Markov measures. So these measures admit actually two equivalent descriptions. So first, let me begin with the description as Markov measures. So suppose we're given a finite alphabet. And suppose that it is endowed with the structure of a topological Markov chain, so that we have a certain admissibility matrix, which is matrix with zeros, with entries 0, 1, so that transition between elements A and B is allowed if and only if the corresponding matrix element sigma AB is equal to 1, and otherwise this matrix element is equal to 0. Okay, and now in this situation, it turns out that one can define a Markov chain on this state space by using fewer parameters than usually, because usually in order to define a Markov chain, we need a whole matrix of transition probability, the whole transition operator. Whereas here we already have a certain matrix, and therefore we can use it as a kind of skeleton. And therefore, the probabilistic ingredient will be, instead of being two-dimensional, will be just one-dimensional. So that now one can define the transition probabilities in the following way. Suppose that we have a probability measure on our alphabet, and then just from this probability measure, I can define the transition probabilities in the following way. The transition probability from A to B will be just the value of this measure at the point B, at our target. But of course, I cannot do like this because I have additional restrictions given by my admissibility matrix. And therefore, I just have to normalize these numbers so that my transitions will only happen when they are allowed by the admissibility matrix. So I have to normalize by dividing, let me denote it by sigma arrow of A, where, not sigma, theta arrow of A, where this theta arrow of A is just the sum of all values of our measure taking over the letters from our alphabet which are admissible starting from A. Okay, so that's therefore in this situation, well, I have defined transition matrix. I have defined a transition matrix, and this is what I will call a multiplicative Markov chain, multiplicative Markov measure. So the difference, once again, is that here our set of parameters is one-dimensional. It's just this vector, one probability distribution, and additionally, I'm using the admissibility matrix. I'm using the admissibility matrix. Okay, now it turns out that measures like this actually admit a natural description in terms of what is called the Radon-Nikodym problem. So since here there is this combination of two names, Radon and Nikodym, this definition obviously refers to Radon-Nikodym derivatives. And, well, I think that's the terminology which was introduced by Klaus, right? In paragraph 10 of your book from 1977. Okay, so suppose that we have on the same state space X, we have two measures. Let's say lambda and I don't want nu, lambda and nu. Okay, and then well, if these measures are equivalent, which means that they have the same null set, then it means that there exists the corresponding Radon-Nikodym derivative. And now suppose that we are talking about the situation when our state space is endowed with an action of a countable group. Okay, then if we start just from one measure, then we can consider the family of its translates. And a measure is called quasi-invariant if all these measures are pairwise equivalent. Okay, and in this situation, therefore, since all these measures are pairwise equivalent, we can consider the family of the Radon-Nikodym derivatives. And then this family of Radon-Nikodym derivatives satisfies the cocycle identity. Or in other words, it produces what is called the Radon-Nikodym cocycle. And now this Radon-Nikodym problem is, in a sense, inverse to this definition. So suppose we are already given a certain cocycle of the group action on our space. And then the question is whether there is a quasi-invariant measure whose Radon-Nikodym cocycle will coincide with the given one. Okay, so given a cocycle, find a measure with the prescribed Radon-Nikodym with the prescribed Radon-Nikodym cocycle. Okay, it's a bit awkward. So we are given a cocycle, and we want to realize as the Radon-Nikodym cocycle of a certain measure. Now here one can consider a slightly more general situation. Namely, instead of a group action, we can talk about a countable equivalence relation. Of course, the particular case will be when our equivalence relation is just the orbit equivalence relation of a certain action, and there is a kind of general nonsense result saying that any barrel equivalence relation can actually be generated by an action of a certain countable group. Okay, so the advantage of this notion of passing to equivalence relations is actually the fact that, quite surprisingly, the notion of equivalence of measures, or the notion of invariance and quasi-invariance, and even the definition of the Radon-Nikodym cocycle, in fact, has nothing to do with the presence of a group. And it can be defined just in terms of the orbit equivalence relation. So we don't really need a group in order to talk about these things. We can just talk about an equivalence relation. Huh? In this formulation, of course, because I don't have almost everywhere. I don't have almost everywhere yet, so yeah. In this setup, when talking about equivalence relations, then one can actually use the following notation for the cocycle. So that's just, let's say, delta lambda. So it depends on 2 points. And slightly metaphorically, this Radon-Nikodym cocycle is just the ratio of the differentials of our measure at 2 equivalent points. Well, this notation is actually more convenient than the group notation, because with the group notation, of course, one can write down with some not much of an effort the cocycle identity. However, in this situation for equivalence relations, the cocycle identity looks really in the simplest possible way, because here we just take the ratios of infinitesimal ratios of our measure at 2 different points, and then the cocycle identity here just takes the form of the, well, that's the same chain rule, but it's written much more conveniently like this. Okay, so that's the usual chain rule, and the general definition of a cocycle in this way, if I'm talking about equivalence relations, is just like this. Okay, and now let me consider one particular situation which will provide the promised link with the multiplicative Markov measures, which is the following. So let's now consider the one-sided shift, the unilateral shift associated with our alphabet with this admissibility matrix. So let's consider the corresponding topological Markov chain. So how do I denote it? A that plus sigma, so that's the set of all sequences such that all the transitions here are admissible. Okay, so this will be our state space. This will be our state space. And in order to talk about cocycle, I will need an equivalence relation. And for this equivalence relation, I will take just the asynchronous tail equivalence relation. So I will say that two strings like that, they are equivalent if they coincide starting from a certain moment, maybe up to a shift. Okay, so that's, let's say, x, that's x prime, and in this situation, I will say that x is equivalent to x prime. Okay, and now how does one define cocycles in this situation? Actually, in this situation, it's much easier because one can easily see that the whole orbit of any point, the whole equivalence class of any point, can be obtained if we are allowed just to take the following operation. If we pass from the point x to its shift. Okay, so what is the shift? The shift is just the result of removing the first coordinate. So that's a unilateral shift. And of course, any point is equivalent to its image under the shift. And now it is a simple observation that actually, in order to define cocycle, what we have to do, we just have to prescribe its values on the pairs like this. Okay, so if I have a cocycle, then I can always consider this function, which is what is called potential of the cocycle in this situation, right? And conversely, if I have any function on my state space X, then I can, by using the cocycle identity, one can easily see that one can extend it uniquely to a cocycle of this equivalence relation. Okay, and now well, I wouldn't call it a theorem, but let's call it observation, that okay, let me still call it a theorem. That if we have a multiplicative Markov measure, or a multiplicative Markov measure, then it is quasi-invariant with respect to the asynchronous tail equivalence relation. And its Radon-Nikodym derivative, its Radon-Nikodym cocycle. It has the property that, okay, the potential of its Radon-Nikodym cocycle potential of the Radon-Nikodym cocycle depends only on the first letter. So that's a function on our topological Markov shift on the space of sequences, which only depends on the first coordinate. The potential of the Radon-Nikodym cocycle depends on the first coordinate only. And conversely, if one is given a potential which depends on the first coordinate only, then it doesn't always give us a measure with the corresponding Radon-Nikodym cocycle. So there is a certain, well, algebraic relation, which is easily to write down. But if this algebraic relation is satisfied, then the Radon-Nikodym problem is solvable, and the corresponding measure is Markov multiplicative. So let me give one example, which will actually be my main example, which is the following. Now I will be talking about groups, so let me take the free group with two generators, A and B. And then there is the boundary of this group, which is the set of irreducible words in the alphabet, which consists of the generators and the inverses. And this is precisely what I have described here when talking about the topological Markov chains. So here the alphabet A consists of the letters A, B, A minus 1, B minus 1. And the admissibility matrix is determined by the condition that we don't have any cancellations. So the pairs A minus 1, A minus 1, A, B minus 1, B minus 1, B are not allowed. Not allowed, and all the other transitions are admissible. So that's precisely the set of infinite irreducible words. Irreducible words. And in this case, actually, our asynchronous tail equivalence relation is nothing but the orbit equivalence relation of the action of the free group on its boundary. That's the orbit equivalence relation of the action of our group on its boundary. Okay, so and in this situation, therefore, what do we have? We have one-to-one correspondence between probability measures on our set of generators and multiplicative Markov measures, subject once again to this relation, which I didn't want to specify. Okay, so the moral being that, let's say, it is useful to consider these multiplicative Markov measures. Actually, they were introduced and reintroduced by many people on many occasions. And apparently, none of these people really knew about each other. So the first one was no one else than Bill Perry in '64 in his paper where he introduced topological Markov chains. These measures were called piecewise linear processes. Then these measures appeared in, so that's mid-60s. Then in '85, there was a paper by Evans who was interested in sister algebras, and there these measures appeared under the name of quasi-product states or quasi-product measures. Then they appeared in '97 in a paper by Klaus Schmidt and Peterson. There was no name for these measures. They were called just Gibbs measures with first coordinate potential. And that's precisely the measures which are simultaneously invariant with respect to the shift and the adic transformation. And then finally, at the beginning, in 2005, they were reintroduced by Jean Mérès from entirely probabilistic considerations. He was interested in random walks on free groups. Okay, so that was some background on these multiplicative Markov measures, and now let me turn to the second half of my talk, where I will talk about the singularity of stationary measures. The problem which I'm going to address is quite natural. Suppose we are given a compact space. And suppose that we have a continuous transformation. Well, it need not be invertible, just a continuous map of our state space to itself. And then according to the Boголюбов-Krylov theorem, or rather Krylov-Boголюбов, well, that's what, 35, I think. This transformation will always have an invariant measure. There is always an invariant probability measure. Okay, now that's the situation when we were talking about deterministic dynamics. And instead of that, one can make these dynamics fuzzy or Markovian. Namely, instead of assigning to points from our state space other points, That's deterministic dynamics. We can assign to these points probability measures. And, well, here we wanted our transformation to be continuous. That's condition sine qua non, without which one cannot really apply the machinery of Krylov-Bogolubov. And here we also want this assignment to be continuous with respect to the weak star topology on the space of probability measures. So that's extremely natural topology. Well, in particular, if our state space is metrizable, then this weak star topology can be metrized by the so-called transportation metric, which is gathering more and more popularity. Okay, so this assignment is continuous. And then, well, in the same way as in the discrete situation, so that's a generalization, because here what we are doing, we're assigning to any point a delta measure. And here we are assigning, well, bona fide probability measure. And then in the same way, one can ask about the existence of invariant measures. So what does it mean invariant? We can look at this assignment as a kind of transportation plan. That's why the term transportation metric. So it tells us whether a unit mass at any point goes under this transportation plan, what becomes a new distribution. And then if we have a whole distribution on our state space, then if we apply this transportation plan to every point, then we obtain a new measure. So therefore our operator acts on measures, and I will use probabilistic or physical notation, so the operator stands here on the right. Because I can also let this operator act on functions. This will be the dual operator, and then it is convenient to put it on the left. Anyway, precisely the same machinery applies, and there is always an invariant measure of such operator, or in probabilistic language, this is what is called stationary measure. And now let's do the following. Suppose that we have not just one Markov operator, so this P is nothing but a Markov operator. And suppose that we have two Markov operators. Suppose we have two Markov operators, and let's assume that they preserve, there is a certain measure which is preserved by both operators. They have a common invariant measure. So and in this situation, of course, we can take convex combination of these operators. And it will obviously preserve the same measure. Or we can take a composition of these operators, and this composition obviously also preserves our original measure. Now, actually, one can consider the composition also in the deterministic situation. So if we have two transformations which preserve the same measure, then the composition also preserves the same measure. However, if I want to take convex combination of two transformations, then inevitably I will have to leave the realm of deterministic dynamics and move to the realm of Markov dynamics. Okay, so that's in the situation when we have precisely stationary measures. But quite often, quite often, one is interested not so much in the measures themselves, but only in their classes. What happens in this situation? So now let's assume that we have two stationary measures for our operators, and we only know that these two measures are equivalent. In this situation, of course, we cannot construct an invariant measure for a convex combination or for composition. However, one can then formulate the following question. Whether these compound operators, either, let's say, have sum or composition, or actually one can take anything from the convex algebra generated by our two operators. So do these operators have stationary measures? Stationary measures from the same class. Or it may so happen that actually stationary measures are unique for a certain class of operators, and then in these situations, we are talking, well, for each operator we produce the unique stationary measure, and the question is whether it will belong to the same class as the original stationary measures. And that's a very natural question, but I couldn't really find it in the literature. Even in the deterministic case, when one can still ask this question about compositions of operators, apparently there are, for instance, one can look at the certain homeomorphisms of this circle and construct counterexamples to this conjecture like that. However, I wasn't able to find any, well, that's essentially the only situation I was able to find. And anyway, I couldn't find any simple construction of counterexamples like that. And actually no counterexamples in the case of truly Markov operators. And it turns out that such counterexamples indeed exist. And now I will briefly outline the construction. So the construction actually refers to a rather specific situation where, as I have already mentioned, in particular, the stationary measures will be unique. So what is this situation? So I have a hyperbolic group. I have a hyperbolic group, so it can be thought of as the fundamental group of a high genus surface, or just our best friend free group. Okay, and then what's important is that this group has a natural boundary, which is called hyperbolic boundary, and in the case of free groups, this boundary is precisely the set of infinite words. And now the dynamics which I'm considering is associated with so-called random walks. So these are Markov chains on the group itself inside, but they also extend to the boundary. So what is random walk? So we take a probability measure on our group, and then the random walk on the group consists in the multiplication on the right by a new distributed increment. Okay, so in the case when our measure is equidistributed on the set of generators, this is just the simple random walk on the Kelly graph. So we have this Kelly graph, and then what we do at each point, we just toss a coin 2 times and choose one of the 4 neighbors with equal probabilities. Okay, and then it turns out that in this situation, if we have a reasonable measure, if it is not very degenerate, then almost every sample path of our random walk will converge to infinity. Will converge to infinity, and there we will have a certain measure which is called a harmonic measure of this random walk. And this harmonic measure has the following property. It is the unique stationary measure of the Markov chain on the boundary, of the Markov dynamics on the boundary, which is defined precisely the same way. So if we take a boundary point, then we just multiply this boundary point on the left by a random element from the group, sampled from this distribution mu. Okay, and in this setup, the Markov dynamic, the dynamics on the boundary determined by these transitions, it has a unique stationary measure. It has a unique stationary measure. So in other words, in this situation, our Markov operators here, they are represented just by probability measures on the group. And well, convex combination is convex combination, whereas composition is just the convolution of probability measures. Just convolution of probability measures. Okay, so now how do I construct the example? So actually it turns out that instead of the free group, it's much more convenient to take the modular group here. Which is, in other words, the free product of Z2 and Z3. And then if we draw its Kelly graph, so here we have 2 generators, that's A, that's B. So one generator is of order 2, the other generator is of order 3. And then the Kelly graph looks in the following way. So if we start from the identity, well, let's say this is A, and then the order 3 generator will give us a triangle, whereas the order 2 generator will provide us with bridges between these triangles. Okay. So this is the Kelly graph. And the boundary here, in the same way as in the case of free group, will also be the set of infinite irreducible words in this alphabet. So what does it mean? Either we start with A, and then after A, well, we cannot put another A, so it should be either B or B squared, which I denote by beta 1. Then the next letter should again be A, then again either B or B squared, and so on. Okay, so that's one component of the boundary. Let me denote it by DGA. So that's the infinite words which begin with E. And the other component will be the result of the action of our generator A on this set. So this will be the infinite words of this type, which begin with a certain power of b. Okay, so here our boundary consists of two components, so it looks not as homogeneous as in the case of the free group. On the other hand, the advantage here is that actually, well, A and powers of B are alternating, but A is always A, so it doesn't give us any information. And in other words, in order to encode an infinite word, what we have to specify is the following. What is the first letter here, whether we have A or not at the beginning. And then we have to specify this sequence, which is what? Each of these betas is either our generator B or its inverse, or its square. Therefore, here we just have the full shift on two symbols. Okay, so we have two copies of the full shift on two symbols. And it is because of that that now one can easily obtain measures which are equivalent but not coinciding. What are these measures? So I can take the same Bernoulli measure, both on the first boundary component and on the same and on the second boundary component, and then I can play with the weight in the convex combination. Okay, so I can consider therefore the following measures. Let me denote them by kappa, so two parameters, alpha and p. So that's p kappa alpha plus 1 minus p a multiplied by this kappa alpha. So kappa alpha, so alpha and p here are both between 0 and 1. So p is the coefficient in the convex combination, and alpha is just the coefficient which determines the parameter which determines the corresponding Bernoulli measure. So we take b with probability alpha and b squared with probability 1 minus alpha. Okay, so and this so here P obviously doesn't change the measure class, so the measure classes will be parameterized by this number alpha, and I will call these measure classes, okay, so that's kappa alpha P, that's the Denjoy class, Denjoy alpha class. Okay, so why the name of Denjoy? Because actually these measures were first introduced by Denjoy in 1932. And the reason was the following. So Denjoy was interested in the singularity problem, in its more classical aspect, namely he was interested, in that time it was still a novelty, he was interested in modern language in measures of full support on the unit interval, singular with respect to the Lebesgue measure. So at that time it was still a novelty. And as Denjoy himself describes in great detail, he was given a topic on this, he was giving a talk on this topic in Paris in 1931, and Adamar, who was in the audience, pointed out that an earlier construction of Minkowski could be useful for Denjoy. So what is this construction? Minkowski actually So Minkowski (1904). In that time, he couldn't talk about measures because the measure theory didn't exist. That's precisely when essentially the measure theory was created by Lebesgue. However, what Minkowski had defined, he defined his famous interrogation mark function. He defined it for entirely number theoretical considerations. However, this interrogation sign function is nothing else than the cumulative distribution function of the Denjoy measure with the parameter 1/2. Is the distribution function of the measure with the parameter 1/2 restricted onto the interval 0, 1. Because Minkowski, of course, he didn't, well, actually, not of course, because this language was already available at the time, and it was already very well known thanks to Klein, that the modular group is a free product of Z2 and Z3. Yes. Yeah, that's what I'm going to say. There is no P here because Minkowski was only interested in the restriction of in functions on the unit interval 0, 1. So here, so far I was talking in symbolic terms, but of course this can also be reformulated in the terms of the action of the modular group on the real line. So the transformation, the generator A corresponds to the transformation with the matrix like this, which is Z going to -1 over Z. And the generator of order 3, it corresponds to the matrix, okay, I never remembered, 0, -1, 1, 0. But what is more important and easier to memorize is what happens with the compositions. And the composition AB corresponds to this matrix, 1, 1, 0, 1, whereas composition AB squared corresponds to the transposition of this matrix. What? Wait, AB, it's this matrix, right?
It's not A.
Sorry. Okay, yeah, there is one missing here, yeah, of course. Okay, and AB squared corresponds to the transposition 1, 0, 1, 1, so that here the transformation is Z going to Z plus 1, and here Z going to Z over Z plus 1. Okay, so, and these are the transformations which map the positive ray. So here we shifted by 1. So the positive ray is mapped onto the ray from 1 to infinity. And here the whole positive ray is mapped to the interval from 0 to 1. So that's precisely what people doing iterated functions like. So in other words, these two maps allow us to subdivide the whole positive ray into two images, one under this transformation and the other one under this transformation. Okay, and now this is all when we are starting with A, which means that actually the positive ray, it's precisely what I will identify with the first components of the boundary. That's the infinite words which start with A. and infinite words which start with the power of b, this will be the second component of my boundary, which in this interpretation corresponds to the negative ray. So that's why there is no p here, because I'm only, well, if I want to follow Minkowski and Denjoy, I will only be interested in the infinite words with, which start with E. And moreover, actually, I even want to restrict my measure to the interval 0, 1, which means that I will even have to fix beta 1, which has to be just B. It has to be just B. Okay, so anyway, that's the identification with the between the symbolic model and the action of the modular group on the boundary. And now, what was the definition of this Minkowski measure, or rather of his function? So one starts with, let's say, 0 over 0 and 1 over 1. Okay, so 0 over 1, of course. So that's the unit interval. Okay, and then in the middle, one puts the sum of the numerators and the sum of denominators. So it will be 1 over 2. Okay, and then one continues like this. So here one should add 1/3. Here it will be 2/3, and so on and so forth. So, and like this, at each step, we will be subdividing each of the intervals of the previous order into two smaller subintervals, and so on and so forth. This is what is known as Ferry or Stern, or, well, there are other names associated with the tree. And then, well, if we start with the whole measure equal to 1, total mass equal 1, then we assign to each of the intervals of the first order measures 1/2, and so on and so forth. So that's precisely the definition of the Minkowski measure. Okay, and now I guess I have to finish very soon. Now, how do I finally obtain the counterexamples? What I do it with random walks, and so that's the identity of the group. And I consider random walks whose step distribution is supported by this triangle. So here there are altogether 6 group elements. Identity doesn't really matter because it only slows down my random walk but doesn't change the harmonic measure. And therefore, altogether, I have 6 parameters. I have 5 parameters and one condition, that the total weight of my measure has to be equal to 1. So I have to put weights here, 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 and here. So I have 4 degrees of freedom. And now the main, well, the key observation here is that no matter when no matter which step distribution I consider here, the resulting harmonic measure actually will always be multiplicative Markov. And multiplicative Markov in this situation means precisely to be one of these Denjoy measures, one of the measures with parameters alpha and p. And so here for free, essentially, just because of these features of the modular group, just because of the presence of these 2 boundary components and of the presence of Bernoulli shift, what do? I have 4 parameters. I have 4 parameters here. I have a variety of dimension 4. But the output, if I look at a fixed value of alpha, for instance, alpha equal to 1/2, then therefore I will have, in my variety of dimension 4, I will have codimension 1, therefore I will have subvariety of dimension 3. And these will be all probability measures which provide harmonic measures from the same class. So there is a lot of them. And then, well, concerning the convex combination, one just has to check that this variety is not convex. That's straightforward. And concerning the product of operators, here one uses actually the following trick. So if I take the product of these two measures, like this, then this is the same as taking the square, convolution square of this measure mu a, which will have the same harmonic measure as the random walk governed by the measure mu a. And then, well, once again, one just have to make sure, and there are enough parameters to guarantee that one can choose our random walk such that its harmonic measure will be singular to the harmonic measure of its right translate by A. So this is the result. The proof is not really very interesting. However, I am not aware of anything which would provide simpler examples. However, what I would like to emphasize that this whole phenomena appears to me to be absolutely new. This fact that one can have two stationary measures which are equivalent, and then when one passes to compound operators, then one leaves the same equivalence class of measures so that dimension can drop and so on and so forth. In general, this phenomenon is completely unclear to me. So what's behind it, whether it works for other groups, I presume it does. However, how, I don't know. It's still very much open. Okay, thank you very much.